Good morning, guys.
Good morning, doctor.
Good morning, doctor.
Okay, how many of us here? 35. Okay, let us start our session this morning with a moment of silence, remembrance our God. Al-Fatiha. Okay, so this is our last week of class. I hope you are happy. You will not see me anymore. Okay. Our last topic is about buckling. What is buckling? Okay. Buckling. Dalam bahasa Melayu, call it, I put it secret first. I don't say it Malay first. Okay, buckling, when thing is, look at this. Tengok ni, tengok ni betul-betul. Saya tarik dia, P. Are you with me, guys?
Yes.
So, sigma is equal to P over E, right?
Yes.
Yeah, let's say this diameter here, the diameter here is 50 mm. Okay. The question is, what is the P that should I put here for it to fill? Let's say the yield, sigma, the material is, yield is, let's say 200 megapascal. So this is simple failure analysis before, right? So what is the P? So the P for yield is P sigma times A, sigma Y times A. The sigma must become sigma Y times the area. So what do we have there? 210 to the power of 6 times the area 50 mm, pi 0.050 square pi d square over 4. Right? So what's the load there? Please calculate it for me quickly.
39.3 kilopascal.
Okay. Kilonewton.
Kilonewton, sorry.
Yeah. 39.3 kilonewton. So this one will yield. That means we reach plastic or reach failure. We don't want it to be plastic. This is normal elastic cases. So now what is, I put this one, compression. Same thing not?
Same thing.
So if the yield is still 200, that means minus 200. So this one is 39.3 kilonewton, right?
Yes.
So the stress is 200 megapascal. So sigma Y here is, sigma Y is 200 megapascal. So far, we assume it compression also minus 200 megapascal, right?
Yes.
That is our yield, right? Now look at this phenomena. Does it care about this long? What about that P over A only? P times A only for compression, right? What about that one? Does it make any difference not? This L1, this L2. L2 is much more than L1. The diameter is also 50 mm. Does it make any difference?
From the calculation, no different.
See? This one have no different. No different. if we are using just sigma is equal to P over A. So, tensile, what about tensile? Tensile. Now from your eyes, this is tensile. And the other one is compression and compression. Which one is more critical? Common sense.
The longer one.
And tensile or more dangerous? Tensile or compression?
Tensile.
Look at this. Take out your ruler. You have a ruler, right? Like that, ruler. Ruler. Put your hand like that. And then put your hand like that. Do it on your own. Everybody, find your ruler. Push it. Because this is too big. I take a simple thing here. Just like a ruler. Compression. Compression there. Push it. So the stress is become bigger and bigger, but less than sigma y. Look at this. Less than sigma y. What happened now there? I don't have any bending. Just compression. What happened to that?
My ruler bend.
There's anything bending force there?
No.
So what is this? What is this calling?
Buckling.
Yes. This is the last topic that we want to learn. This phenomena we call buckling, meleding dalam bahasa Melayu. Buckling. It's not bending. It's only due to tensile compression, not tensile, sorry. It's due to compression load only. Buckling will happen only compression load, not tensile. Pull it, no buckling will happen. You pull it, the failure will fail at sigma y. Are you with me? In
Yes.
compression, it can fail by buckling or it can fail by tensile. You haven't heard about buckling before. If the size is too big, it will fail by, it will never buckle. If the size is too big, it will never buckle. So the failure will be on yield. So where does buckling happen? Buckling happens somewhere here or here. Way before sigma buckling is less than sigma y. That means the load for buckling is less than the load for sigma y. Sigma y is here. Are you with me? The buckling is here. That's why the compression load is very dangerous. Okay. Now we talk about the size. If it's too big just now, like this one, it's too big, so it's difficult to buckle, right? If it is slender, like your ruler, buckle, right?
Yes.
So that must be something to do with the cross-section size, right?
Yes.
Okay. What about the length? Short and long. Which one is easier to buckle?
Long.
Yes. So we have the diameter size. We are talking about the diameter. We are talking about the size. And now, I take a ruler. One is metal ruler, one is plastic ruler. Which one is easier to buckle?
Plastic.
The material also. Something to do with easy or not to buckle. The size of cross-section also something to do easy or not to buckle. And the length is also easy or not something to do with to buckle. Are you with me, guys?
Yes.
So now we know a little bit about buckling. Buckling will happen at what? Long material, slender, that means not big, thin. Thin material, long material, and soft material. So how do we put it into formula? So this guy, he's a mathematician. Propose the solution to find this one. What is the load for buckling? Huh? So we just have to memorize this formula. Very simple formula. What is the load for buckling? Some people, PB is P buckling. Some people put it PE. PB is equal to PE. E is Euler. This is the, still remember the Euler formula in mathematics? Still remember the name of Euler in mathematics?
No.
You forgot already. Differential equation. Okay? So we use the PU, Euler. So in France, we call it Euler. But we call it the spelling is Euler, that one. No problem. PE. So what is PE? PE is to detect when is the load to buckle. Euler said PE is equal to beta pi square EI over L square. See that? The higher the E, difficult to buckle. The softer the E, the less the E, the easier to buckle. Understand now what we discussed just now?
Yes.
The cross section I, the bigger the diameter, the bigger the I, difficult to buckle. Less diameter, less I, easy to buckle. Understand now?
Yes. Understand now.
And then the longer the material, the bigger the bottom here, the easy to buckle. Because the bigger the bottom, the less at the top, right?
Yes.
The shorter the material, bigger at the top. So difficult to buckle. So what we see by our eyes just now is proven by this Euler. Are you with me?
Yes.
And then what is to find that sigma buckling? Very easy. That P Euler divided by the A. We got the stress for buckling. That stress must be less than sigma Y. If the stress is higher than sigma Y, that means what? Buckling will never happen. Sigma Y will happen first. Are you with me?
Yes.
If the stress is less than sigma Y, that means buckling will happen. So how do they predict? When we know the length, the size, when you know the size, material, and this is connection. Beta is connection. There are 4 types of connection. What is that? Everybody memorize this first. What is the formula? PE? Beta pi square EI over L square. This is pi square is constant. 3 point something square, almost 10. The value here is around 10. So, beta pi square EI over L square. So the square is only at the bottom. This is not square. Can you remember this formula, please?
Yes, can.
To predict when it's buckle. Buckle happen when?
Before yield.
Under compression load only. Buckle can happen and cannot happen during compression. So if we know the size, we can predict the stress, whether it is below or higher than the yield. If the below the yield, it buckle. Are you with me, guys?
Yes.
Okay. Compression, load. Buckling happen when what?
Compression.
Only in axial compression. Not bending, not torsion, not shearing, but axial load. But the axial load must be in compression. If tensile load, there's no buckling happen. Only fail with yield. If the compression load can fail by buckle, or it can fail by yield. If it is too short, fail by yields. This is long, fail by buckle. If it is too big, fail by yield. It's too small, fail by buckle. Very big material, not buckling. Yield. Are you with me, guys?
Yes.
So what is beta? What is beta? Beta is the connection. Beta is only 4 value of beta. Beta can be the value of 1/4, 1, 2, 4. Put aside 1/4 first. 1, 2, 4. Then you understand. What is 1, 2, 4? If the connection is pin and pin, load compression, this is pin, pin. So beta is 1. So the buckling shape is like that. Are you with me, guys?
Yes.
Huh? And then beta is 4. This is built in. This is built in, but also compression, also compression. Try to make at your ruler. You can see that one. Pin and pin. Shapes like that. But if you build in there, squeeze it there, squeeze your ruler and push it. The shape is like what? The shape is like this. Correct me or not?
Yes, yes.
So more load to deflect this than this one. So this one beta is 4. 0 slope here, 0 slope here. Here we got slope value. Here we got slope value. You see that?
Yes.
So more difficult to buckle this one. If you have built-in and built-in. So this is 4 times harder than this. What is in between? In between is, this is pin. So this is built-in. So the shape will be like that. Right? So this is beta is equal to 2. 1, 2, 4. Easy not to remember?
Easy.
1, 2, 4. This is 1 and 4. Half of that is 2. Right?
Yes.
So where this one, 1/4 of 4. 1/4 of 4 is different from this. This is open system. Open system is like this. So this one can twist to the right. Are you with me?
Yes.
The other one just now cannot twist to the right, just in line, because they are fixed to the point. This one, there's no fixed point at the bottom, only at the bottom. So this one can move to the right. So this is much easier to happen. Why is that? This is called beta is equal to 1 to 4. Much easier. That means less than 1. Free end. This is free end. Are you with me, guys?
Yes.
You must understand what is free end and pin. The pin cannot go to the left and right. The pin cannot go to that, just up and down. But this one free end can go to the left and right. Are you with me, guys?
Yes.
So this is much easier to buckle. If they can move to the left and right. 1/4, the value here. So 4 value only. Depend on the connection. Normally, most of the connection are pin and pin. So 1, beta is 1. Okay, clear with me, guys?
Yes, clear.
Yeah. I want to make a simple. What is the size of that pen, roughly?
1 centimeter, 1.5.
What is the diameter of that pen?
150 mm.
150 mm. No. Good. Roughly, your thumb, that one. What the diameter of your thumb?
Yeah, between
Yeah.
1 and 1.5 centimeter.
So in mm is what?
15 mm.
15 mm. Very different from 150, you know. Are you with me, guys? Do you know what is your measurement? 15 mm is very different from 150 mm. Okay. So diameter, let's say 10 or 15, right? Mm. Just hypothetical. So this is, let's say this is 10 mm and your beam is 1 meter length. It's made from steel. Pin and pin. This 1 meter length, L is 1 meter, diameter is 10 mm. This is made from steel. The Y is 200 megapascal. The E is 200 gigapascal. Correct? Correct me?
Yes.
Now we put under compression. Does it yield or not? So what is PE? Pin and pin. P Euler is beta pi square EI over L square. So what is your beta? Pin and pin?
1.
1. Pi square. Your E is 200. Still 210 to the power of 9. Your I is round. So pi 0.010 pi d to the power 4 over 64. Correct?
Yes, correct.
And then over L square. Your L is 1 meter. So what is the value there?
969. Only.
9?
69
What?
Newton.
Somebody else, please push calculator. Is that correct?
Yes, same.
Okay. Now we check the yield. We check the stress. What is sigma E? This is just a formula to predict. But the validity, we have to check the yield, the stress must be less than sigma Y. So to predict only. Not everything is buckle. Just the prediction. So now what is sigma E? Sigma E must PE over area. So PE is 969. Sorry. 969 divided by the area. Pi 0.010 pi square over 4. So what is the value there?
12.3 megapascal.
12.3 megapascal. Now go back to the graph. Go back to the graph to understand it. This is 200. Half of it, what? 100. Half of 100 is 50. Are you with me, guys?
Yes.
Half of 50 is 25. Half of 25 is 12.5. This somewhere there. See that? Now, can you see how dangerous this is?
Yes.
A new failure happened, even though it's not yield yet, but it buckle. Buckle mean when you release the load, it buckle, huh? See that? Buckle. When you release the load, it become normal back. It's not failure. It's not broken, you know. Are you with me not?
Yes.
I'm not talking about broken. Buckle and then release, go back to the origin. The yield is, because the yield is not 200, the yield is 12 only. Nothing failure happen here. But, now imagine, the pillar of the Penang Bridge. When the lorry, heavy lorry comes together there and the pillar buckle for a while, and then when the lorry move, it coming back. Is it okay? Is it okay?
Seems okay.
No.
Runtuh lah kalau dia buckle. Faham sayang? Are you with me? It's not okay. We don't want it to buckle. Do you allow the beam, the bridge to be like that? You're top and then go back. You allow it to happen?
Oh, cannot.
So, semua ke atas tu akan runtuh walaupun tiang tu tak patah. Are you with me?
Yes.
So we don't want it to buckle. So this one become what? New limit. Not that anymore. Are you with me?
Yes.
The failure limit is not yield anymore, but that buckling limit. Can you imagine now? Only 1 meter length. This size is 10 mm, 1 meter length. So it buckle at 12 megapascal. So now change it to bigger. That is 10 mm, right? Are you with me?
Yes.
10 mm. Now put that one become 50 mm. What is the look there? 50 mm, 0.050. What is the look there? Come on, what is the value?
606 kilonewton.
606 kilonewton. Is it true? Somebody else?
Yes.
Okay. Now put the value here. 606 times to the power of 3 and put the size here is 0.050. Why the stress there?
308.6 megapascal.
Again, 3
08.6 megapascal.
megapascal. Somebody else prove it. Is it true?
Same.
So now 306 megapascal. 306 is here. Will that be happen?
No.
The material only up until 200 megapascal only. The material. The theory is 308 now. Will that happen not?
No.
So that thing will not fail by buckling. It will fail by
Yield.
yield. See that? 50 mm here will not buckle if the length is 1 meter. 10 mm buckle. You see that?
Yes.
Now you understand why we have to check. So this one will not happen also. Why this one will not happen? It's already will
Because
fail.
buckle will not happen.
Buckle will not happen. It will fail before this. It will fail by. It will fail by
Yield.
yield. What is the yield? What is the yield load? P yield is equal to sigma yield times A. So sigma yield is 200 times 10 to the power of 6 times the area. Pi 0.050 square over 4. So what is the value there?
393 kilonewton.
393, around 400, right? Around 400 kilonewton filled by
Yield.
yield. To buckle, if it requires 600, so will never happen because it already failure already. By the normal failure. The normal failure is what? Yield lah. Are you with me, guys?
Yes.
What we are afraid is just the failure before yield. The failure at yield, we already take into consideration when we are doing failure analysis, correct?
Yes.
So we take a new consideration is the new limit, the buckling. You understand the whole concept now?
Yes.
I give you the real size, 10 mm and 50 mm. 1 meter length. One will buckle, one will not buckle. That's the real size, 10 mm and 50 mm. Are you with me, guys?
Yes.
You see that? The stress is there, the other one is here. So it's not logic. So the normal failure by yield will happen. So this is the main concept of buckling. What's the theory? Euler theory. Simple theory. What the theory say? Beta times pi square E times I divided by L square. What is that? To predict the load when it's buckled. When we know the length of the beam, when we know the size of the beam, we know the material of the beam, we know the connection of the beam, we can predict when the load is buckling. Divide by the area, we can know the stress. We can compare, or this is logic or not. So this mathematician predict the buckling load. P Euler. Very simple formula. Beta times pi square EI over L square. That is load, Newton, Are you with me, guys?
Yes.
It take consideration the material, it take consideration the size, it take consideration the length. Okay. Just now, 1 meter, 12.5 mm. 12.5 mm, 1 meter in buckle, right? For the 1 meter length, for the 10 mm. Now let us do, we cut it short. The 10 mm just now, cut it short. 1 meter become, 1 meter now become, this is 10 mm. The length is 20 mm. So, what is the buckling load? P buckling again. Beta square, beta pi square EI over L square. Beta is 1, that's pin and pin. Pi square, E is 210 to the power of 9. And then, I pi 0.0, diameter still 10, 10, 1 0 to the power of 4 over 64, and the length now is 0.20 is what? 0.02, right? Square. What is the value there?
2.42 meganewton.
Still very big, 2.42 meganewton. Mega, very big. So what is the Euler there? What is the sigma there? 2.42 10 to the power of 6 divided by the area. Pi 0.010 square over 4. Pi d square over 4. What is the value there?
Very big. 3.08 times 10 to the power 10.
So 330
30
gigapascal, right? 30,000 megapascal, right?
Yes.
Way before here. So this formula valid not?
Valid.
Not valid lah. above the yield.
But then won't buckle ma. No lah.
This is what I call the formula is not valid for buckling. That means it's not buckle. Are you with me?
Oh, okay.
So it's not buckling, right?
Yes.
Just now, 1 meter one, the same size, buckling at load is, the stress is 12.5 megapascal, right?
Yes,
It changed from
12.2.
1 meter into 0.0220, the same size. This one not buckle, this one buckle. Can you see that?
Yes.
So that's why we have to check the size carefully. Are you with me, guys?
Yes.
It's not something to do with diameter only. Combination of diameter, combination of length, combination of material. Are you with me, guys?
Yes.
So that is a combination. The whole thing is that one combination. Siapa yang paling selamat? Orang pendek dengan orang gemuk. Dia stabil. Correct. Orang kurus dengan tinggi, dia kurang stabil. Senang cerita lah. Pendek dengan gemuk, I besar dengan L pendek. Right? Kurus tinggi, senang melending. Gemuk pendek, susah nak melending. Itulah basically kita punya summary of that. Okay. So those are the, how do we relate with the load? Now, how do we relate with the load? Simple. All the, let's say we have here, and then they put load there. This one is, and then put a load there. So this is how relate with the load, not? So let's say this A, B, C here, but B and D here can buckle not? A, B, C is bending. We're not concerned about that. And then B and D can buckle not? Yes. So the question say, let's say diameter here is 1 meter, and the diameter is 20 mm. 1 meter, 20, also, let's say this is 0.8 meter, 20 mm. 20 mm, 0.8 meter. So, buckle or not? We have to check. Let's say this is steel. So, what P max can I put that one? So, this is 1 meter, this is 2 meter. So, this is 1.8 meter here. Okay, no problem. So, what do we do? This is the type of question or loading that you have to find in real life. So, this is the bridge. This is the support of the bridge. Are you with me, guys?
Yes.
So this support here. So what do we do? A simple mathematics. Simple mathematics. Do that one first. That one first. Before you do the loading here, do that one first. How much this one can withhold only? If this one buckle, what as the maximum load can be put there? So what is that? Do that one first. What is that? P, B, E, P, B, D, Euler. Is that correct or not?
Yes.
Pin and pin, 1. Pi square, EI, 200 10 to the power of 9. And then your I is 20 mm. 0.020 pi d square, pi d to the power 4 over 64. Your L is 0.8. So what's the load there? And then what is sigma load there? Want to check that one is below sigma yield or not? Or not? That one create first. What is P Euler there, please?
24.2 kilonewton.
There, put here. 24.2 10 to the power 3 divided by area. Pi 0.020 square over 4. So what is your stress there?
77 megapascal.
77 megapascal. Below Y not?
Yes, below Y.
Yes. So it can buckle not?
Yes, can buckle.
So it can buckle. So confirm. confirm this one can buckle. So the load maximum go here is 24 kilonewton here, right? The maximum can go here 24. If there is 24, what is this? So go back to static. Draw back the free body diagram. What is the free body diagram there? Pin there. So there's a reaction here. PBD. So that is your PC. PC going down. 1 here, 2 here. Some moment at A. Summation of moment at A must equal to 0. Put your hand there. Okay? PBD times 1 is equal to PC times 3. So PBD can only hold maximum 24. Are you with me?
Yes.
So 24 there, 24.2 kilonewton there, times 1 is equal to PC times 3. So PC here, what is the maximum that can hold? What is that?
8.07 kilonewton.
8.07 kilonewton. So the answer, PC must be less than 8.4 kilonewton for it to be safe. This one must be less than 8.4 kilonewton for this not to buckle. This is a simple calculation. Are you with me, guys?
Yes.
Harder than this. The same question, put in a different. So this is being pushed that way. PC, the holding part is not straight. The buckling part is not straight. The buckling part is bending, something like that. So this one push, this one is back. Under compression not. A, B, C, and B and D is under compression not.
Yes.
Static. Let's say the angle is 40 degrees there. So this 1 meter, 2 meter, this 0.8 meter. No problem. 0.8 meter maybe short. Okay, no problem. Okay. Part angle 40. So how you draw the? I know that one 0.8. The maximum is 24. We have done just one now, right?
Yes.
So what is the relationship for that? It's all about free body diagram. Static, static, static. Are you with me, guys?
Yes.
PC. So this diagram here break into two. So this is PBD. This is PBD. So PBD become P-Euler. So this is PBD. PBD 40 degrees. So there is AX, AY there. You see that one?
Yes.
You see the diagram there?
Yes.
I don't have to draw that one anymore. This one is included into that, right?
Yes.
And then, can I get the relationship? Same thing, moment there. 1 meter and 2 meter there. Summation of moment at A is equal to 0. So break that PBD into two. What do we have there? One is axial, one is going upright. PBD, this is 40 degrees. Why is that?
Sine 40.
Sine 40 degrees. Why is that one? PBD cos 40. PBD cos 40 is going through that line. Doesn't give any more moment. PBD sine 40 is going to that. Get moment not?
Yes.
Yes. So what is the equation? PC times 3 is equal to PBD sine 40 times distance 1. Correct?
Yes.
So I know that one is can only hold 24 kilonewton, right?
Yes. 24.2.
So can I solve this? Yes. What is PC? PD sine 40 divided by 3. So 24.2 times sine 40 divided by 3. So what is the way to do that?
5.2 kilonewton.
1.2 kilo.
5.2.
5.2. So just Yeah. Put here, this one can only put 5.2 kilonewton. Just now, this one we put it straight. This one can hold up until 8 kilonewton, right?
Yes.
We bend it like that. So this one is not 5.8 anymore, 5.2 kilonewton. 5.3, this one collect by buckling. That's the meaning. This is how you put into relation. Are you with me, guys?
Yes.
What are the other example of buckling? This cross section of this load here is not solid rectangular. It's not solid rectangular. Can I have the cross section like this? Can I have?
Yes, can.
Can I have cross section like that? This one.
Can.
So what is the difference there?
Different in I.
I. Now, here what I do we have? I is what? Pi d square, pi d to the 4 over 64, right?
Yes.
Your I about that one and that one is the same, not?
Yes, it's the same.
So no problem. What about this one? I about this one and I about this one is the same, not?
No.
So which I do I choose? Look at look at your ruler just now. It is easy to buckle that way or that way. This is your ruler. Yeah? Put that. So you buckle that I or that I. AA or BB.
AA.
AA is less than BB, right?
Yes.
Look at the formula. P Euler is pi square EI over L square. So your I must be the lowest I. Are you with me?
Yes.
The lowest I, we got the lowest E, right? The lowest P. So this is the lowest I. So this is the lowest I, not this I. Tak percaya tengok. Kalau ni 10, ni 1. Kalau I paksi ni what? I is equal to B d cube 1 times B d cube 10 to the cube over 12. B d cube over 12. Correct? What about I about that axis? This is XX. I about YY is equal to 10 times 1 to the cube over 12. So 10D. Are you with me?
Yes.
What is the value here? The top one is the bottom one. This is 10 squared, 1 cube. 1 cube is 1. 10 over 12, roughly 0.88. This one is 1000 divided by 12, 88. Or this is 1, this is 100. So this is 100 times stronger than this. Are you with me, guys?
Yes.
So this is much stronger than this one. So if we buckle at the less stronger I. Are you with me, guys?
Yes.
Dia tak boleh buckle ke sini, tak apa, dia buckle ke sini. Itu maksud dia. Ni yang lemah punya I, dia buckle kat sini. This is stronger I, cannot buckle that way. Are you with me, guys?
Yes.
Still buckle at the start kat mana? Start yang stronger. Start yang less stronger lah. So what do you do in this case? If you have a cross section that is not symmetry, you find the less I in the formula. Are you with me, guys?
Yes.
Same thing with this. You buckle it that way or that way first. I don't know. Which one is stronger? Is that correct?
Yes.
You put that way. Can I calculate I about that way? Yes. Can I calculate about that way? Yes. So which one is less? Use that I in the formula. Are you with me, guys?
Yes.
Kalau dia bulat, sama je lah. Mana-mana pun sama, correct?
Yes, correct.
Outside minus inside. So for this case, I don't know which one is higher, which one is less. So use the less one. Calculate both and use the less one. Are you with me, guys?
Yes.
So that's about it, the loading. Loading boleh straight, boleh bengkok tak? Boleh. It's just all about static equation. Are you with me, guys?
Yes.
So that's about it. Nampak tak? Kita dah cover dah. In very short lecture, kita dah cover almost 80% of the point. What is the point today? We know how to predict when they are failure. Euler theory, right? And then we have to check the sigma E. Whether it's below or above yield. If above, cannot use that formula. Right?
Yes.
And then we relate with the loading. The loading at the here is different loading to here. So, but this one will create this one buckling, right? How we relate the loading with the buckling here. Don't be trapped. If I put this one is the other way around, will this one buckle not?
Yes, will.
No, this one will be in tensile. Tensile, no buckling. That's why you have to understand your static very quick. Tarik ke sana, this is tensile not?
Yes.
Tensile will not buckle. The failure will be in yield. Are you with me, guys?
Yes, yes.
Must have very sharp mind. Akal ni yang collect all this information. We talk about the tensile and compression. And we talk about this compression. And this is compression. When you put that way, why you lost this is compression? Because your akal is not asking yourself. Are you with me?
Yes.
Okay, we stop that today. Okay, I think we cover quite a lot today. When it start to buckle, the cross section, the smallest eye, we compare different thickness, we compare different length. What else? We are different size, different shape of cross section. What else? Tensile and compression again. Yeah? Okay, clear? So we
Yes,
know
clear.
to find the limit of the load for it not to buckle. So buckle is a new failure now. Not just yield. When it's compression, you must check first. Can fail by yield or it can fail by buckle. Okay, are you with me, guys?
Yes.
Okay, thank you very much for today. I give you some exercise homework to calculate the buckling. Okay, Assalamualaikum. See you next Wednesday. Okay,
Thank you, Doctor.
Thank
Thank you so much, doctor.
Thank you, doctor.
Thank you, doctor.
Thank you, Doctor.
Thank you, doctor.